Today we discuss section 4.7 Euclidean quadratic fields. First we prove that the ring of integers O of Q of root D for D is equal to these numbers is a Euclidean domain. All of these ring of integers are Euclidean domain with Euclidean evaluation this n of A. In order to prove this Q of a ring of integers O of Q of root D is Euclidean domain, we need to prove that this phi is a Euclidean evaluation. In order to prove this phi is a Euclidean evaluation, we need to prove this. Here, if alpha, beta are elements of non-zero elements of O, then norm of alpha, modulus of norm of alpha less than or equal to norm of modulus of beta. Then we need to prove that for non-zero elements of O, we have alpha equal to for non-zero elements alpha beta belongs to this. We have gamma and delta belongs to O such that alpha equal to beta gamma plus delta, where either delta equal to 0 or the evaluation of delta is less than evaluation of beta. So the first statement is very obvious. But because we know that every element of O, norm is a positive integer. Okay? So norm is an integer, modulus of norm is always a positive integer. So whenever alpha divides beta, we can get this beta is equal to lambda into A for lambda belongs to O. Then norm of beta is written as norm of alpha into this lambda, then norm of alpha into norm of lambda, that is equal to modulus of norm of alpha into modulus of norm of lambda. But these are all positive integers, hence this norm of alpha is always less than or equal to norm of beta. Okay, so this is alpha here. Norm of alpha is always less than or equal to norm of beta. So first statement is very obvious. To prove the second statement, we will prove an equivalent statement for this B. Okay, we will not prove this B directly, but first we prove an equivalent statement for this B, and we will prove that statement for this the statement B. The equivalent statement is this: for any epsilon belongs to Q of root D, there exists K belongs to O such that norm of epsilon minus K less than 1. Okay, so this is the property that if we consider Q of root D and consider ring of integers of Q of root D as O, then we choose any element from here, any element K belongs to, so I'll write this K first here. Any element epsilon belongs to this, you can get, if you consider disk of radius 1 using this n, you can get at least one element K belongs to O. Okay, this is in some sense this is some kind of denseness property. If any element epsilon, every neighborhood of epsilon with radius 1 contains an element of O itself. Yeah. So this is a nice property of this Q of root D. Then this is equivalent to B. That is what we have to prove. So first we prove B implies C. Okay, so B implies C means assuming this holds, then we will prove for any epsilon belongs to Q of root D there exists K. Okay. For this we need to refer lemma 2.11. I'll explain the lemma here. If you choose any element epsilon belongs to Q of root D, then there exists a non-zero C such that C epsilon belongs to this O. That's the idea here, that C is an element of non-zero element of this Z. That means if you take alpha equal to what we have to prove is epsilon belongs to Q of root D, we need to get an element K. Okay, this is our idea. So we write alpha is equal to C epsilon and beta is equal to C. These are non-zero elements of O minus O, then these are elements of O minus 0. Then assuming B, you can get two elements, gamma and delta, in such a way that alpha can be written as gamma beta plus delta. Okay, with the property that we have two conditions, either delta is equal to 0 or the evaluation of modulus of norm of delta is less than no modulus of norm of this beta. Okay, so if this is the case, if delta equal to 0, what happens? This alpha equal to gamma beta. What is alpha? Alpha is C epsilon, and beta is C again. So this is gamma C. Okay, so this implies epsilon equal to gamma. Okay, because C is non-zero quantity, you can cancel because this is an integral domain. So from this you can get, if this is the case, delta equal to 0, we can get epsilon equal to gamma. Okay, then we let k is equal to epsilon itself. Okay, or we can write it as this. If you let k is equal to epsilon, you can get k is equal to gamma. But we know that this gamma and delta are elements of O. Because of this B, we can say that gamma is an element of O, then k is an element of O. So k is an element of O, we can get this n of this k is nothing but this gamma. We can say that this k and gamma, k and epsilon are same, because gamma and epsilon are same. So we can get norm of this quantity as 0, then norm of 0 is 0, then modulus is always less than 1. That is trivially true. On the other hand, this equation becomes alpha is equal to gamma beta plus delta, implies alpha is CE. So CE is equal to C beta plus delta, with the property that modulus of norm of delta is less than modulus of norm of beta. Okay, this is the argument here. But we know that norm of modulus of norm of delta by C. Okay, delta by C is less than 1, because C is same as this beta. Now this implies norm of delta by C is less than 1, implies norm of, what is delta by C? That is norm of modulus of norm of delta by C. From this equation, delta by C is epsilon minus k, epsilon minus beta. So this is epsilon minus beta is less than 1. So we take beta as k. So for any epsilon belongs to the square of root d, obviously this beta is an element of O, then we can get an element of O such that epsilon norm of epsilon minus b k is less than 1. So this shows that B implies C. Now we will prove C implies B. Then we can say that B and C are equivalent. To prove C implies B, we take this epsilon as epsilon is equal to alpha by beta. Okay, clearly this epsilon is an element of Q of root d. Then by C there exists k belongs to O such that modulus of norm of epsilon minus k is less than 1. From this you can write modulus of norm of alpha by beta minus k is less than 1. This implies modulus norm of alpha minus k beta by norm of beta. By taking LCM, norm can be splitted less than 1. So from this you can write norm of alpha minus k beta less than norm of modulus of norm of beta. Now we let this delta is equal to alpha minus k beta. Okay, from this you can write what is alpha. Alpha is equal to k beta plus delta, but we know that modulus of norm of beta, uh, substitute for this alpha minus k beta first, that is norm of delta, then that is less than modulus of norm of beta. Okay, so this shows that B holds. That means B implies C and C implies B are same. That means B and C are equivalent. So now we will prove the condition C. That means every element of Q of root D, we will find a nearest element in O. That means if you consider a element K such that modulus of norm of epsilon minus K is less than 1. Now we will prove C for the values D is equal to minus 1, minus 2, minus 3, minus 7, minus 11. These are the values. In these values, we can partition these values into two, set to minus 1, minus 2, because these two values are congruent to, not congruent to 1 mod 4, and rest of the values 3, minus 3, minus 7, minus 11 are congruent to 1 mod 4. In these two cases, we have the ring of integers are classified into two different manner. In this case, ring of integers are z of root d. These are the values of d, and in this case, z of half plus half root d. So we need to consider these two cases separately. First, we assume the values of d are minus 1 and minus 2. So we have d is not congruent to 1 mod 4. We have ring of integers is z of root d. So if we consider any r plus s root d with r comma s belongs to a rational number, we need to find out k. The form of k is x plus y root d with x and y are integers. Obviously, this norm of any element in this O is or Q of root D is norm of k can be written as x square minus dy square. This is the norm of k here. Then clearly norm of epsilon minus k is nothing but modulus of this is modulus of this one. This is same as this one. Okay, so we need to find for any epsilon, we need to find k such that this is less than 1. So in order to get this k, we plot that r and s here and take the nearest integer from this r and s. Okay, say this is x and this is y. Okay, so this is the nearest integer of this r, and this is the nearest integer. In order to get the nearest integer, you need to consider an interval of radius half. Okay, within the radius half, you can get an integer for any r. Similarly, from s, then you can write r minus x square. That is the distance between the square of the distance between r and x. That is same as that one. So you can get that is half square plus 2 times half square, because d is either minus 1 or minus 2. So if you consider minus 1, that is strictly less than this quantity, x square plus 1 s minus y square. This is less than or equal. So whenever we prove this is less than 1, you can easily get, in the case of d is equal to minus 1, this is also less than 1. So in the case d is equal to minus 1 and minus 2, you can easily prove this one using the nearest integers of this r and s. So this proves C in case d is equal to minus 1 and minus 2. Now we can prove the second case for the values d is equal to minus 3, minus 7, minus 11. These are congruent to 1 mod 4. Therefore, the ring of integers of q of root d takes the form z of half plus half root d, or you can write it as this is same as z of x or you can write it as zeta for x plus y, this quantity, 1 plus root d by 2 with x comma y are integers, z. So this is z of this one. So any arbitrary element k takes this form. Then we need to find out for epsilon is r plus s root d. Corresponding to this, we need to find an element k such that modulus of norm of epsilon minus k is less than 1. So that implies this, when you simplify this one. So we need to find x and y such that this holds. Okay, so first you mark r and s here. Then first you write what is 2s. You plot 2s, then take the nearest integer of 2s as y. So you can write it as modulus of 2s minus y is always less than half, because when you take a interval with radius half, you can get nearest integer of 2s. So from this you can write 2s minus y square is always less than or equal to this 1 by 4. Okay, that is the idea here. So once you choose this y, then you can plot r minus half y somewhere over this real line. Okay, so using this number, choose an integer nearby this number. We already have chosen this y. Using this y, you can plot r minus half y. Then from this you can choose x. Then clearly we can say that r minus half y minus x is always less than or equal to half. Then its square is always r minus half y minus x square is always less than or equal to 1 by 4. Using these two factors, you can get this value, that is always when we evaluate this modulus, that is this one, you can say that this is less than 1 by 4 and this is less than 1 by 4. When you replace the values of these are minus 3, minus 7, minus 11. Okay, when you replace this d by minus 11, that will be the maximum. Okay, rest of them are this is less than or equal to this quantity plus 7 square of this, and which is again greater than or equal to modulus of plus 3 square modulus of this square plus 3 times the square, that is always less than. So we need to consider the expression with d is equal to minus 11. Then you can get that will be 1 by 4. This is 1 by 4 plus 11 times this is 1 by 4 again. Okay, so we'll get this is equal to, I'll write this expression, that is equal to 1 by 4 plus 11 times we have here 1 by 16, because we know that this quantity is 2 by 2s minus y is y square is always less than or equal to 4. That means this quantity s minus half y, so that is always less than or equal to 1 by 4 into 4. You can take this 2 out, then 4 can be taken out from this bracket, then that will be less than or equal to 1 by 16. That's why here 1 by 16. Then this will be 1 by 4 plus 11 by 16, that is equal to 15 by 16, that is less than 1. Okay, this shows that C is true in case of D is equal to minus 3, minus 7, minus 11. So in all cases we can say that these are B. Obviously B is always true if C is true. Then in all cases we can say that these are Euclidean domains.